All right, welcome back. In the first video, I explained to you the background related to the lab and why we chose to drop coffee filters. We chose to drop coffee filters because they are very, very light and they reach terminal velocity very quickly. In this second video, I'd like to share the data with you and then go over the data analysis that you will have to be doing. So let's start with the data. So I went to the top of the ladder in my living room and I had a stack of 7 nested coffee filters just like this. So there's 7 of them in this little pile. And I dropped this whole thing. But before I dropped it, I put them on the electronic balance and I measured the mass. And the mass was 6 grams. So we can obviously convert that into kilograms. And then we can multiply by 9.8 to come up with newtons. And I did that once and it was 0.0588 newtons. Alright, so then I went to the top of my ladder, and the top of my ladder was 1.914 meters. And I dropped that stack of coffee filters and measured the time it took to hit the ground. And that happened to be 0.71 seconds. Ideally, I would have dropped it 3 times to hit the ground, 3 times, and then averaged my time to make sure that I get really, really good data. But you'll never know if I really did that or not. All right, so then I went down off the ladder and I picked up my pile of coffee filters and then I peeled one of them away, and now I only have 6 coffee filters in my stack. So I put that back on the electronic balance and it was 5.2 grams. And then I dropped those. What's going to happen to the time when I drop fewer coffee filters? So my stack now is lighter. I hope you can see that, like when you drop a light feather, it kind of floats down, and so the time actually becomes longer. So it was not surprising that it took 0.77 seconds. Then I peeled off another coffee filter, and now I'm only dropping 5 of them. And then I dropped 4 of them, and then 3, and then we'll just go down the column. It'll probably be a lot easier to write the numbers down here. All right, and the very last coffee filter had a mass of just 0.9 grams. And because the weight of the coffee filters became less each time, the time actually became longer. So 0.85, 0.98, 1.05, 1.34, and when I had only 1 coffee filter, it took 2.0 seconds for that to reach the ground. All right, so you can see that I'm going to get the grams are going to go to kilograms and kilograms are going to go to newtons. So you should be able to fill in those very, very easily. All right, but look at the next column. The next column says average terminal velocity. Well, as I explained in the first video, the reason that we dropped coffee filters is because they're going to reach terminal velocity like almost instantaneously. So basically, I can just find the slope of this line, which really is just the distance over the time. So constant velocity, distance over time, and that constant velocity is the terminal velocity. So quite simply, average terminal velocity, VT, equals distance over time. So this distance column divided by this time column. So you can get those values very, very easily. And this says average terminal velocity squared in case it ended up being a squared model. So this is just going to be VT squared. So you square these numbers and put those there. All right, right now I'm not going to worry about this or this. We'll come back and kind of explain this part near the end here. All right, so what do I do with this data now? So this kind of goes back to the purpose of the lab. The purpose of the lab was I had to figure out what kind of model, what kind of drag is happening on coffee filters. So to figure that out, I'm going to have to make myself a graph so that I can choose the right kind of model. All right, so I'm going to look at this a little bit more carefully here. So the drag model, because it was at terminal velocity, I was able to replace the FD with an FW. So that was right here. FW then became an mg equals kV. And so this is in my y position, k, and then my x position, y equals mx plus b. So that tells me that I'm going to do a graph of, I want FW to be on the y-axis, so FW. And then I want the v, the plane velocity, to be on the x-axis. And then when I graph my data, the slope of the line is going to turn out to be k. So let's go back and look at the data. What does that mean? So what I mean by that is you're going to graph this FW. These are actually going to be y values. So I'll say y. And plain old v, plain v. These are going to be your x values. And I would also then do linear regression to put your best fit line on there. And I would turn on your correlation coefficient because that's going to be helpful when we have to choose the rightful model. All right, the second graph that we're going to have to make then is the second model. So the second model has an FW on the y-axis. It's got a v squared on the x-axis, and then the slope is going to be k. So this is going to be FW. This is going to be v squared. Plot my points, a little bit of linear regression, r squared. All right, so you're going to have two graphs. And so how do I know which model is the one that best approximates coffee filters? So what if, I'm just making this up, what if this correlation coefficient was 0.9555? And what if this correlation coefficient was 0.9888? Well, yeah, this then would be the winner in terms of the model. So that's how you're going to figure out what model best approximates your coffee filters. So the second purpose of the lab then was to find the coefficient of drag. So let's pretend it's this model, and I don't know if it's going to turn out to be that model or not, honestly. So if this is the model, I'm going to write that down. I'm looking for my purple pen. All right, so this is going to be y equals kv squared. So this k, which is the slope of this line, really was this whole mess. So I'm going to expand that out. So FW, which is equal to the FD because we replaced that. And now I'm going to expand out the K. So that's going to be 1/2 the coefficient of drag, the cross-sectional area, the density of air, and V squared. This is the K. Well, the second part of the lab is I'm supposed to find the coefficient of drag. But I can get the K value from my slope. So I'm going to write down slope equals K. And K is going to be equal to 1/2 the coefficient of drag, which is what I'm looking for, times the cross-sectional area, which we haven't found yet, and the density of air. And the density of air is 1.29. And so that was over here, the density of air, 1.29. Now this, instead of filling them out here, we're going to kind of figure them out over here. So A is cross-sectional area. So in the notes the other day, I kind of drew a picture of something that was like a tube. So if you had a tube flying through the air, this would be the cross-sectional area. Well, instead, we have a coffee filter being dropped. So I'm going to draw a picture of a coffee filter. I'm kind of exaggerating it here. So the problem is my coffee filter has a big cross-sectional area up here at the top, and it has a smaller cross-sectional area down here at the bottom. So the first thing I did is I want to get those two values. So I took my ruler here, and I measured my cross-sectional area going across here, and it was kind of, back when it was neater, it was close to 13. So I'm going to write down 13 centimeters. And then I can turn it upside down and I can measure the smallest one. We'll call it 8.5, 8.5. So we have something that's not like a consistent tube. So I guess for lack of anything else to do or anything better to do, we're just going to average it. We're just going to use the middle and call this the cross-sectional area. So when I average 13 and 8.5, it averages out to 10.75 centimeters. So I need to plug in the A value though. So the cross-sectional area is going to be a circle, which is pi r squared. So it's going to be pi, and the radius that I'm going to use is that 10.75, but I'm going to convert it into meters. And this is the A value that is going to go in there. So again, if you know your K value, which you can get from your graph, you then would have everything that you need to calculate the coefficient of drag. And we know coffee filters have drag. That's why they're reaching terminal velocity very quickly. So it's a really good lab to have to calculate a drag value, because if I dropped a bowling ball off the cliff, the drag might be so small it would be difficult to measure. And that's why we drop coffee filters off something really tall across the country in AP Physics C. So what do you have to do? You have to, I'll say the word, finish the lab, and by finishing the lab you're doing the questions on the last page, and then you also have to submit your graphs, which are these two graphs, which are going to support and provide the evidence for the model that you pick and the work that you do for all of the questions. So I hope that kind of helps you get started on the lab, and if we end up needing to have a Zoom meeting later this week to discuss it some more, we can do that. So get back to me and let me know what you need. Good luck, and we'll talk to you soon.